Okay, let's look at a couple spherical objects and uh, apply Gauss's law. A couple sort of classic example systems that you need to know. So um, the first is, uh, so we're going to be applying Gauss's law. Put it up here. It says that the electric flux through a closed surface is equal to the charge enclosed by that surface over epsilon naught. And the first system that we want to look at, this is an example in your book, is, and actually, let me paste a picture from your book just so it looks a little nicer. I struggle to draw spheres. So here's this situation that I want us to consider. And this is a sphere with charge uniformly distributed through it. So this is not a conductor. This must be some kind of dielectric where you have charge that's distributed just throughout its volume. And it has a total charge Q. And given that, and this thing has a radius R naught, and so as a result, we can define a charge density, which is the charge per volume, which would be, in this case, Q per the volume of this object, 4/3 pi R naught cubed. That's the radius of it. Now, we want to know, or we want to use Gauss's law to find the electric field as a function of R. And there's really two regimes to consider. There's within the sphere and outside the sphere. So there's sort of two zones to look at. We have our, inside and our outside. So inside the sphere, that would correspond to, in the picture, A2, the surface A2. So we're going to imagine a Gaussian surface, a spherical surface, that's a sphere that's smaller than the total sphere. So, or than, in other words, it has a radius that's smaller than R naught. And so in this uh, region, so since we're working with a spherical surface and the charge is distributed spherically, this integral, well, the dot product will turn, since those things are aligned, will just be E dA. And since this is spherically symmetric, E will be constant, and this will just become E times 4 pi R squared. Now, the charge that's enclosed is not going to be the whole charge. It's only going to be the fraction of the charge that lies within the surface A2. So we can write that as an integral over the volume. So this would correspond to the charge density integrated over that volume, the volume that corresponds to A2. Let's see. Let me just put volume of A2. So this, I showed you in a different video about integrating over the spherical, in spherical coordinates over volume. And this is actually the simple case because the volume, or sorry, the charge distribution is a constant. So in other words, this we can pull out of the integral, and then we just have the charge distribution times the integral over the volume, which is another way of saying the total volume within A2. And so this looks like the charge distribution. Actually, let me put it on the line above. This looks like the charge distribution times 4/3 pi r cubed. And let's then substitute in our charge distribution that we stated up here. So this is going to equal Q over 4/3 pi r naught cubed times 4/3 pi r cubed. Notice most of this, or much of this stuff would cancel. And then we have that this E, so we could, well, I'll just write it again here. Ooh, I dropped an epsilon naught somewhere. Q. Sorry. So we would have Q over epsilon naught, and then we would have r cubed over r naught cubed. And notice r squared and r squared would cancel on both sides, and we would be left with, well, here, I can move this up a little more. We could divide through by 4 pi, and we would find that the electric field within the sphere is going to equal Q r 4 pi epsilon naught r naught cubed. So this is for r less than r naught. So the behavior, the thing so everything in here is constant except for r, so this is actually proportional to r when you're within the sphere. Now we can contrast that to the situation when we're outside the sphere. We have the same starting point. Now, this is the simple problem that we've already looked at a time or two. The symmetry arguments still apply. So E dot dA, since E and the area vector, on that surface are always with a spherical surface centered and surrounding a spherical distribution, or a spherically symmetric situation. This will just give us E times 4 pi r squared. And now this is simple because the charge enclosed will just be the total Q, or epsilon naught. And this is our familiar by now electric field due to a point charge. So this is, it looks just like a point, although it's not. It's, a ball. It has volume. But when you're outside of it, it looks like a point, as if all the charge was, concentrated at the very center. And this is for r greater than r naught. And we could, write this, we could make a little, and the behavior of this goes like 1 over r squared, like we talked about before. So what this looks like as a function of r, the electric field, is it increases until linearly proportional to r until you get to r naught, and then it's going to drop off. It's going to drop off like 1 over r squared, like a point. And that maximum value that it's going to be able to attain would be, when R equals R naught, this becomes the max value is going to be Q, or the R naught cancels, over 4 pi epsilon naught R naught squared. So this is a pretty classic example of applying Gauss's law to a situation where you have just um, evenly distributed charge in a sphere. And let's compare this to a very similar situation. Which is a conductor. So imagine like a metal ball now. And you'll have to forgive my picture is not going to be as good, but this, so imagine we basically are doing the same analysis, but now it's a metal ball. So it's like a ball of copper or something. And we would have an interior Gaussian surface. Let me see if I can draw this a little bit. Oh, man. An interior Gaussian surface, we can call that A, and an exterior one, B. You're going to have to take my word for it that these are supposed to be spherically symmetrical. Let's again say that our sphere has a radius of R naught. And let's again charge it with Q. Now, if this is a conductor, what's going to happen is the charge is going to accumulate all on the surface because recall the charge can move more or less freely. And so it's going to try and get as far away from all the other charge in this as possible because like charges repel. And so it's going to collect on the surface. Now, what that means is that when we look at this for our two regimes here, inside, this problem, this problem becomes very simple because notice there is no charge that's going to be enclosed within surface A because it's all on the surface. So this would become 0. And so as a result, the electric field must be 0. So in contrast to outside of this thing, now when we're out beyond R naught, this becomes the same familiar problem. So looks like the enclosed charge. So now the enclosed charge is just the total, whatever's on it. We just Q. And then again, this is the same situation where we have the spherical distribution and using a sphere commensurate with it as our Gaussian surface outside of it, this would just become E 4 pi r squared. E is Q. So this is for E r greater than r naught. This is for E r less than r naught. Now, so we can kind of put our picture, let's put it up here, just to contrast. So a conductor with the same size and the same charge, it's going to have nothing on the inside for an electric field. And then once you get to R naught, the electric field is going to drop off like 1 over r squared. And it's going to have the same behavior It's indistinguishable from the dielectric with the charge distributed throughout its volume when you're outside of the volume. Inside they look different, outside they look the same. So this is kind of a nice example. Just it shows you, two different contrasting objects and how when you're far away from them, when you're outside of them, it doesn't matter. They look like the same thing. They look like a point. But inside, a conductor and a dielectric would have different electric field behavior.